between them. So I have a sample problem here. We have a solution made with 1.2 grams of ethylene glycol. We've given the molecular formula there. And this solute is added to 4 kilograms of water. That's our solvent. We want to calculate the molality, the mole fraction, and the weight percent or mass percent. Now, we're going to need the molar mass of ethylene glycol, so let's do that first. We pull all the pieces out there. There are 2 carbons, there are 2 oxygens, and there are 6 hydrogens. So let's add those up together because we're going to need that before we get into the problem itself. Now, carbon's 12.01, so 2 carbons would be 24.02. Oxygen is 16, so 2 oxygens would be 32. And hydrogen is 1.01, so 6 hydrogens would be 6.06. So if we add all that together, 0.8, 2, 1, would be 62.08 grams per mole for ethylene glycol. Now water, we've seen quite a bit. Water is 18.02. We'll just incorporate that when we get to that part of the calculation. Now, considering that we're given masses for both of the components, the weight percent or the mass percent would be the easiest one to start with. So if we start by calculating the weight percent here, the definition we talked about above, this is grams of solute, so that would be 1.2 grams of our ethylene glycol, right, divided in by the total mass of the solution. So 4 kilograms of water would be 4,000 grams of water plus another 1.2 grams of ethylene glycol would be 4,000 and 1.2 grams total. And since this is a percent, we'd multiply that ratio by 100%. So if we plug that into the calculator, 1.2 divided by 4,000 and 1.2 is 2.99 times 10 to the minus 4th. Multiply that by 100, since it's a percentage, right? And now it's 0.02999. Now, because of the 1.2 gram mass of the ethylene glycol, we only have 2 sig figs, so we should round our answer to 2 sig figs. So that would be 0.030. And then since this is a percentage, we want to put the percent sign there, but really no other units to show what is being described there. They kind of cancel out back here in the way weight percent is put together. Okay, so 0.030% for that solution. Now, the next easiest one to do, since we have the masses already, would be molality. So let's do that second. Now, molality is moles of solute divided by the total moles, moles of the solvent divided by kilograms of, I think I said it wrong again, moles of solute divided by kilograms of solvent. So we've already got kilograms of solvent, that was given, so let's change our grams of ethylene glycol to moles, so we can use that in the molality. 1.2 grams of ethylene glycol, we already calculated its molar mass. 1 mole is 62.08 grams. 1.2 divided by 62.08 is 0.01933 moles, keeping a couple extra digits there before we round up the final answer. So, if molality is moles of solute per liters of solution, then I can plug in how many moles of my solute there are, divide that by how many kilograms of solvent there are, the 4 kilograms of water, and that's molality. Now, molality is a lowercase m, but it's an italicized lowercase m. It's kind of hard to write an italicized letter, but when you see it in the textbook, you'll see the italics. That kind of helps you distinguish molality from something like meters, which is a regular unitalicized m. So 0.00, that's my answer in the memory, so just divide that by 4, and that's 4.83 times 10 to the minus 3rd. Now, it again is only 2 significant figures, so I'm just going to keep the 4.8 times 10 to the minus 3rd for my answer. That would be the molality of that particular solution. Now, the last one would be mole fraction. And And like we said before, mole fraction is abbreviated with the capital letter chi, it's kind of fancy X. So this is going to be moles of the solute divided by total moles of the components of the solution. So we already figured out moles of the solute, the ethylene glycol. We're going to need moles of water here as well. So if I have 4 kilograms of water, that's 4,000 grams of water. And 1 mole of water weighs 18.02 grams. Which means that we have 221.98 moles of water. So the mole fraction would be how many moles of our solute there are, which would be what we calculated above. So that would be 0.01933 moles of solute. And that's going to be divided by 221.98 plus 0.01933. Now that's a pretty small number compared to 222 moles, but it won't always be so small. This example is just a fairly low concentration. So if I plug that in, 0.01933 divided by 221.98 plus 0.01933, that gives me 8.7. Times 10 to the minus fifth. Okay, and there's no units on mole fraction because moles cancels with the other moles that we're dividing by. But that gives us a much smaller number there for that particular concentration. Okay? Now, one of the things that you're going to want to be able to do, and this will come up when we start to have some assignments, is interconvert between these units. So I think you should be able to, if I give you one of these, you ought to be able to change this to another one. For instance, if I give you a weight percent, right, since you know the 100, that would be 0.03 grams of ethylene glycol for every 100 grams of water. You could easily start turning that into moles, for example, or into volume if you had the density, and you could extract from the weight percent what the molality of the solution is or what the mole fraction of the solution is. Something like that. Now, the last thing on this page, which will be the last thing in this particular section of the video, is just some terminology. So we're probably fairly familiar with the word soluble or the concept of solubility. We talked about this in terms of solubility rules last semester. Soluble describes materials that will mix together and make a homogeneous solution. So soluble is how we would describe a solid like a salt, whether it dissolves in water or not. It's also how you would describe something like a gas dissolving in water, how soluble is, say, oxygen gas in water. Miscible is really a very similar term, and it has basically the same meaning. Miscible is just generally used to describe liquids. So if two liquids mix together, we would usually describe those liquids as being miscible. Right? Liquids that don't mix, so two liquids like water and alcohol, for instance, mix together, they're miscible with each other. Liquids that don't mix are immiscible. So IM at the beginning of the word. So oil and water, for example, would be immiscible liquids. Now, technically the term miscible could work for solids or gases as well, but it's usually not used that way. So primarily, if you're talking about liquids, you use miscible. If you're talking about gases or solids, particularly if they're dissolving in a liquid, you would use the term soluble. All right, end of that page.